Burnishing tools. They're awesome. They can turn your average finish into the smoothest you've ever seen. They can even work harden the material a little bit, which is another nice benefit. Or even take off those last microns for the perfect fit. They're also great for winning your spindle bearings, and they only work if you push them just right. That's right, I'm not a fan. So today, we're gonna make a different burnishing tool. One that won't ruin the bearings on my lathe or on James' lathe. One that makes a flawless finish on the first try. One that just works better. Welcome to another Toolroom Takeover. As usual, we start off by roughing the stock. We need to cut off the excess material as fast as possible, and the bandsaw is perfect to save some time, tooling, and sometimes even big chunks of metal we can use elsewhere. Then the roughing and mill comes in, and this is where we start seeing some straight lines. The finish is terrible, but our part slowly starts taking shape. This part of the process is often called chasing the part, or chasing the mill, at least around here. James is the one I drew this time, Claw 42. Naturally, I wasn't too thrilled about it. Don't get me wrong, I love James. The problem is, it's not easy to come up with a gift idea for James. He's done so much of everything. Manual machines, CNC conversions, lasers, printers, welding. He's seen bad and average tools and thrown them all in the trash.
Surprise!
He's gotten to a point where he only keeps the good stuff.
He might be right.
So what can you possibly make that has a chance to impress someone like James? Just to prove a point here, my first idea was to make an Arduino clock, the engineer's clock. I have everything figured out, but then
I want to build a mechanical clock that's driven off of a GPS time source.
that was weird. Then I thought about a really fancy can opener. Something different, something out of the box that didn't belong in the shop.
Some of the drawers actually do warrant.
See what I mean? Look at that! It's a freaking Mitutoyo can opener. At that point I was like, burnish it. Now I'm gonna make whatever I want, and if James already has one, that's the one that goes in the trash. The idea for this burnishing tool came from this knurling tool. There's a shank, a column, two arms and a clamping mechanism. It works by pinching the stock on opposite sides, top and bottom, and that completely eliminates spindle bearing wear. On a small lathe, that's the only way to go. What we're seeing right now is the machining of the shank and the column. They will be a single part, and that's where the problems start. Because making a tool for a lathe on the other side of the world, without being able to measure anything, is a bit of a gamble. I was counting on using mine as a reference, as both lathes look pretty much the same, but after checking his videos, they really aren't. The cross slide is different, the tool post is different, and the solid riser is also different. Luckily, I know a guy, and that guy got me James riser block CAD files. After that, a multi-fix model from GrabCAD, a couple emails to Pewee Tools to verify some dimensions, and I got a pretty accurate model of James' setup. And that's when I realized the arms I designed wouldn't work, because the solid riser would be in the way. Moving the tool forward to get some clearance created another problem, which was not being able to get it on center. Not vertically, like a turning tool, but on the horizontal plane, the x-axis. I don't think this would be a problem for James. From what I've seen, his lathe seems to have a lot more travel, but on my lathe it was definitely a problem. We can't take any chances here, so I decided to offset the shank to the side. It looks a bit strange, but you know how it is. It's just a safer bet. I can't have James telling me the tool doesn't fit. So let's talk about machining. I'm cutting these round pieces from a big chunk of pre-hardened 4140. I've used this stuff before, but for some reason this particular batch seems tougher to machine. Which doesn't help matters, as the next part is, on its own, the most challenging part I've ever had to machine. It's not really a complex part, especially if you have a CNC, but keep in mind that my machines are all manual. They're also small and not really made to handle tougher steels. Also, this is mostly a mill project and mine doesn't have a DRO, nor power feeds, so it gets tiring really fast. So sooner or later, I'll have to stop and do something about it. Anyway, laser engraving. Why? It's a great way to see the part before it exists. I know we have 3D printers and there's nothing better for prototyping, but when it comes to seeing the part inside our piece of stock, while we machine it, having some outlines really helps prevent screwing up. Machining this part is all about the order of operations. When you design something, you have to consider the execution, the machines you have, the tools you have and are able to use successfully, the material, the setups, and like I said, the order of operations. I think I found a way through all the features, but if for some reason something doesn't work out the way I'm planning, I'll probably have to start over. And that's very time consuming. There's no Ctrl-Z, people. Even though I have the layout laser engraved, I'm not using it for exact feature location. And that's because the lines from the laser are not very precise. Certainly nowhere near as precise as the ones you can lay out on a surface plate. This first hole will not exist on the final part. It's a shallow, 10mm location hole that will help me avoid indicating the part later. It will also have the important job of trapping the part on several setups, to make sure it doesn't move. Next, I'm drilling a 6mm hole centered on the location of the pivot hole. The final hole will be 8mm, but right now I'm only going to 6 to match my clamping hardware. Now is also the right time to take care of the bottom hole for the clamping mechanism. And finally, we drill a couple of 4mm holes to press out the bearing. Again, when you design something, it's nice to think about maintenance as well. But which bearing? This bearing. In case you're not familiar with burnishing tools and what they do, they use a very hard ball or roller to compress the material after it's being turned. So the tiny ridges left by the turning operation are smoothed out and the finish is usually spectacular. In the home shop, people usually default to the most basic design for this tool, which is just running a ball against a standard bearing. The problem with standard radial bearings is that their outer races are not made to take loads. We have better options, but as always there's a compromise: size and price. So I landed on these. They have 2 rows of balls for better support, and the outer race is thicker. Thicker and grooved, which is kinda nice to keep our carbide ball on track. The next operation is obviously making the bearing pocket. I'm spot drilling what will become the center of the pin. This isn't super precise, since it's just roughly aligned with that shallow hole on the bottom, but it should still help me indicate things faster later. Again, this will not be on the final part. I wasn't counting on having problems making this pocket, but it turned out to be a really stressful operation. So, we're machining an integral pin right on the arm, and the bearing will enter from the side. Now, that represents a series of machining challenges. The pocket is pretty deep, at 18mm, so if you try to take it easy with smaller end mills, you'll run out of cutting length pretty fast. But I saw this coming and bought a longer one. And I broke it immediately. On closer inspection, it doesn't seem to be broken, so I don't know what that was. But I also don't feel like I should keep using it, so let's change the strategy. A size up in diameter also means more cutting length. Inevitably, I had to return to the longer end mill. It's almost like I'm feeling it bending, despite the light cuts. Anyway, I still need to clear the wall so I can use another end mill to plunge the bottom to full depth. I definitely don't want to plunge with this noodle. So I grabbed a standard 6mm, which I had to extend all the way out of the collet, and just started plunging. Once I got to full depth, I swapped to the longer one again to finish the entire wall of the pocket. Great. So I ended up finishing the pocket with a bigger end mill, which means the pocket is now oversized. That's not a problem for the bearing, because I'll use the ID to press it in and the OD is just clearance, but it does mean I'll have less meat later for the holes around the bearing pocket. Not great, since the original design is already tight on that dimension. Eventually I got it done, and although the finish is far from perfect, I moved on to acceptance pretty fast. This pocket took a lot longer to make than I was expecting, and I'm starting to feel the schedule falling behind again. Things really need to go faster from now on, or I risk not having the tool done on time. Again. So far, we've been focused on machining clearance. We've reached the final depth and OD, but we haven't brought the pin to size yet, so you might be wondering what we're doing on the lathe. We're finding out that the initial plan doesn't work. When I was designing the arm, I had in mind turning the pin on the lathe and holding the stock on my 4-jaw chuck. But there's playing things in your head and reality. It's not just that this jaw is held by only one thread, which is dangerous enough on its own, but the jaw also doesn't have enough support to stay square. And the result is the stock being held by just a couple of tiny edges. Now imagine this letting go at 800 RPM. So you go to option number 2, which should have been option number 1 from the start, the milling machine. The problem is how to actually do it. The bearing ID is 8mm, dead on, and I want a light press fit. We're talking about making this pin at +5 to 8 microns. If you're wondering, just imagine a human hair. On average, about 70 microns. So I want to nail a dimension that's 10 times less than that. I could use a small boring bar on my boring head, but I don't think I have enough control to achieve that kind of precision. Plus, there's a bunch of problems to retract the tool, and also to stop at the right depth. Then there's also a thread at the end of the pin. No, I don't want to drill the pin and fit a screw. I want an external thread. And I even made a driver for my threading die. But let's be real, that's just asking to ruin the part. So for all these reasons, I don't want to do this on the mill. If I didn't have to make it myself, and that's the whole point of Toolroom Takeover, I'd just ask today's sponsor to do it. I'd simply upload the CAD file to PCBWay's website, select the material, a fine finish, cause James deserves the best, and all the other details like threading and fillets. A few days later, the parts would be at my door and life would be much easier. That's what PCBWay can do for you. But that's not all. If you don't want to deal with the mess that comes with resin printing, they can handle that for you. And the same goes for sheet metal fabrication. And of course, we can't forget electronics in PCB manufacturing. So if you're stuck like I am, and you're not making a gift for Toolroom Takeover, just go to PCBWay. The link is in the description. Thanks to PCBWay for sponsoring this video. It took me a while to remember I have a faceplate, which I never used. But then again, that could turn into a dangerous operation very quickly. So all I have to do is make it not dangerous. I checked this piece of stock on a surface plate and it looks fairly flat. We're fixturing the part. After drilling for a couple of cap screws, we now have an adjustable way to hold the part on the faceplate. But I was still so concerned with something failing that I overdid the thing. This spacer isn't really needed, but having the part bolted directly to the faceplate feels like extra insurance. Then we take advantage of the spot created earlier. I saw this on an Adam Booth video many years ago. Basically, we indicate the dead center on the front of a live center. The dead center acts like a floating needle, with one end grounded to the spindle axis and the other following the stock. This method is just an approximation though. I still need to indicate directly on the pin. Checking the face is also good practice to make sure the part is square to the spindle axis. I don't know if this happens to you guys, but the more I check, the more I find things are not as they were supposed to be. This time, the part was not square to the spindle. At the beginning I thought the problem was the spacer at the back, but it wasn't. It was still crooked after removing the spacer. I even checked the stock to make sure it wasn't that. But like always, when you cut corners, you get what you deserve. Turns out, the flat piece of stock wasn't flat after all, and I was spending a lot of time chasing problems again. The quick fix for this is machining the fixture in place, so that's what we're doing. It sounded great, but the finish is a different story. Despite the ugliness, this chatter doesn't compromise the goal, so let's move on. Any imperfection at this point should not impact the final tool. I was still a bit nervous though, and my main concern was the actual workbench bouncing back and forth. So to even the rotating mass and reduce the vibration, I added this chunk of steel to the setup. It might just work. I made this dummy bearing in advance. The ID is a couple of microns over, basically the size I want for the final pin. Since I have no good way to measure the pin, This should help gauging the size as I go. In case you're wondering, a micrometer will not fit here. I can barely squeeze in my calipers and those don't have enough precision. I guess all that's left is going by feel. I'm really surprised this setup is working so well. This 5-minute adjustable carriage stop is making it very easy to nail the depth. You can't see it yet, but I'm leaving a small step at the end of the pin. That's to make sure the bearing doesn't run against the wall. Also, the turning tool is leaving a small radius between the pin and the bottom of the pocket. That's much better to avoid cracks than having the sharp corner created by the end mill. For the next step, we need a broken carbide bit. Remember the thread I mentioned earlier? We're going to single point it, as soon as I find this bearing. Yeah, let's make a custom tool. Next, I clenched my butt cheeks and went for it. And there's my relief. Butt cheeks released. To create the threads, I'm going to use this micro threading tool and thread away from the chuck with the lathe in reverse. I decided to plunge straight in. The compound angle was just too awkward to deal with. And again, I have a dummy nut to gauge the fitting. This was actually threaded with the same tap I'll be using to thread the cover. And that's our pin finished. Next we're gonna tackle the bearing cover. It's a simple part with just one specific detail. The OD must be perfect. I'm actually lapping the cover to the arm, and the reason for that is because I want the pin to find support on the threaded end, just in case it starts bending under pressure. After parting it off, we have the cover pretty much done, so we can go back to the arm. The next part is really scary. Not because it's dangerous, but because from this point I'll start losing references. First, a big roughing operation on the front, followed by a finishing operation, which wasn't actually the finish. Because once chatter decides to show up, it's really hard to get rid of it. Look at that, looks like a 3D printed jar. Eventually I managed to make it smooth again by taking light cuts from the top. Then I didn't touch it anymore and went and did something else. I was dreading this part of the job. I don't have much experience matching radii, and I quickly realized what a nightmare it was going to be. So I reviewed my machining plan and decided to go for the big radius next, top and bottom. Now remember when I said my machines are small? Well, a 100mm radius might be asking too much. And silly me quickly discovered I don't have enough travel on the mill to locate the part correctly. So, it's all going to be done by eye and 3D prints. Feel, eye, and 3D prints. Isn't that the foundation of machining? So I'm roughing the part the best I can before we try another sketchy setup. And this time I'll finally use my boring head. The plan is to have a 100mm fly cutter cutting the radius. The plan is also to not have any chatter. I have to start slowly because the roughing operation left lots of peaks, but so far it looks promising. Yeah, it's working. Shit, what now? No way. I'm pretty sure some of you predicted this. So if my boring head unscrews from the arbor in this direction, it means I need to turn it in the other direction. And that's a problem because I don't have a left-hand boring bar. I could try to make one, but I can't spend the entire project making tools. Now that I think about it, I might have another solution for this. And no, it's not flipping the boring bar. That solution involves modifying this chuck adapter for my rotary table, because it can be a faceplate adapter too. That's right, we're growing this rotary table. Honestly, I thought this 250mm faceplate would be too big, but think about it. After the 100mm radius, there's only 25mm of material left to clamp onto. Not a lot. Still, I'm glad it's working. I paid for the hole-end mill, so I'm using the hole-end mill. And now we're in a much better position to start blending the radii. The ball needs to protrude from the bearing housing as much as possible, but also needs to not fall off. The easiest way to make that happen is to have a threaded hole in the retainer cap. Remember, I'm using a grooved bearing, so I can't fit the ball first and the bearing afterwards. And while we're here, we drill and mill a slot for the clamping mechanism. And the same for the column. As for the retainer cap, I'm making it out of bronze. I'll start with the threading, and I need to optimize for them. After all, these will end up held by just a thread or two. So besides having a 1mm pitch again, I ground this 0.8mm relief tool, just to save space. Now that we have enough clearance for the bearing, we can start drilling. After drilling and rimming the 7mm opening, an 8mm ball and mill takes care of shaping the inside. We need a way to drive this in, so I'm slotting the top. And finally, we blend it with the arm. Challenging little part to make. And since we're still on the rotary table, let's take care of the last radius. Milling this corner means losing the last references to the features of this arm. If you didn't notice, it was machined at an angle, and that corner was the last reference to that. I had another go at blending the top, and now I'm happy. The rest, I can do it by hand. But before that, we need to... Oh crap, now it's a broken tap. So this is a 4-degree fixture I was making off camera to finish off the arm. I have 2 days of work invested in this, and breaking a tap is a huge setback when I'm already late. But after the last one I broke, I went looking for tap removal tools. Cheap ones, cause owning the expensive one just attracts bad luck. And I don't know about you guys, but all the taps I've broken so far were spiral taps, and I think I'm starting to develop feelings for them. Honestly, I wasn't expecting much from these, but after a few tries, the broken bit actually started moving. And once you see it budge, you know how it goes. It's coming out, no matter how long it takes. Someone will point out I shouldn't be using a spiral tap on a through hole. Yes, I should, because I just dulled my straight flute, okay? So now I can't wait to tap the next few holes. M2.5. 10 of them. The problem with these arms is that they're too wide. That limits how far you can go with the tool. For instance, you can't get to a corner. I tried to make them as slim as possible, but with a bearing, it's complicated. The next best thing I can do is taper them. 2 planes, 4 degrees each. And since my references are gone, I had to find a way to have them back. Can you imagine breaking a tap after all this work? The final operation is to go from 6 to 8 mm for the pivot pinhole. And if you think this was a lot of work, well, here's the second arm. To connect the arms to the column, we need some pins. I already had these ones, so it was just a matter of cutting them to size. To hold them in place, I didn't want to use circlips. No special reason, I just want the tool to look clean. Press fitting is another way to do it, but I like the idea of easy maintenance. The pins are threaded M5, so I came up with this. A stainless matching plug that press fits into the arm. That way, the pin can be removed as many times as we want. The plug only takes up 2 mm, so the pin is still fully supported on both ends. To drive the pin in and out, I was hoping I could make a slot for a screwdriver with an HSS blade. Yeah, all I managed to do was dull the blade. So, next, I took care of the barrel nut. To prevent an issue I have on my knurling tool, I'm adding the set screw. This stops the threaded rod unscrewing from the bottom end. The threaded rod is actually a commercial 12.9 bolt. I was going to cut the head off, but in the end I decided not to. I just hid it inside the barrel nut. I did thin down the middle section, because otherwise the spring would catch on the threads. And that takes us to these bronze cups. They weren't part of the initial plan. The problem I had was the spring jamming in the slots. I mean, the slots on the arms. I tried to fix it with some washers on both ends of the spring, but the washers ended up jamming as well. And that's because the arms are radiused. It was almost impossible to close the tool. But the bronze cups completely resolved the problem. The big knob will be made from this chunk of brass, big and heavy to make it smooth and satisfying to use. That means it's time to bring the compound back. Cut knurling usually leaves very crisp knurls, so that's what we're going with today. Whoops. That's better. Unfortunately, I screwed up. I don't know exactly what caused this. I'm assuming the knurling wheel left its track due to some run out on the part, but I'm not sure. Anyway, let's try to fix this with the other knurler. It doesn't look good, but maybe it's not lost yet. Last chance to save this, before we go ahead and clean it up. Yeah, square knurling. I do like it. And I know we can see all the imperfections on camera, but it's not that bad. I remember seeing this square knurling on Nick's channel, Jonesy Makes, and this year he's actually the one sending something to me. So I like that. It's like an inspiration chain. The side covers have a weird shape to machine manually, so I took advantage of the Carvera here. Plastic would be a better material for them, but plastic wouldn't make you click on that thumbnail. So brass it is. I'm sure James will take good care of it. They do feel a bit empty though, and we couldn't deliver something to James without his logo. So you know what happens next. The parts are pretty much done, and now we need to take care of their finish. First of all, you might have noticed the lack of chamfers on these parts. I just thought the arms would look weird with them, so I decided not to have any chamfers. That means I have to make sure James won't cut his hands on any sharp edge. I'm constantly fighting flash rust around here, so rust protection is a big deal for me. I know there are some good products in the US to protect machinery and tools, but I can't seem to find them over here. So what I managed to do was this. I cold blued the shank, several runs, including a neutralization one at the end, and then I painted the non-functional part of the shank, and the column. And that's just for looks. Let's not forget we're talking about James. And remember, I want a chance to get these in his toolbox. As for the arms, I began by blending the radius by hand, the old-fashioned way with sandpaper. Once they looked 95% done, I took them to the deburring wheel. I decided to leave the arms with their natural look, including some of the machining finish, but I did use some Renaissance wax on them. Supposedly that should help a little bit with the rusting situation. And all that's left to do now is put it together. Just to be clear, all the burnishing you saw in this video was done with James' tool. I didn't use this one for anything. Second, and someone's gonna ask this, 1/100th of a millimeter. That's the difference in size after burnishing. But keep in mind I didn't have time to run proper tests. As for my gift from Jonesy Makes, that's the biggest mystery. It's been stuck in transit with no updates for many days now. So what I'll do is click right here to find out what Nick sent me. And you should too. Go on, do it. Or, if you want to see if the burnishing tool works on James' lathe, just click here. James, I hope you like it, man. Now if I find out any of you stole my package, remember, I know a guy.